Okay, so this is a variation on the last two that we did. So in this one, instead of like the minimum speed, Sam is going to toss them at 17 meters per second, straight up. And so if Pat didn't catch them at the top, they'd go past Pat. All right. All right. In this case, we're saying, so how fast are they moving when Pat reaches them? All right. So last time they had basically stopped. They had zero velocity when Pat reached them. But that's not what we have this time. Okay. But let's go ahead and make our picture. So our initial speed is 17. So we're going to go up. We know the distance is 12. We do not know the time of flight. We're going to get up here. And we do not know the final speed. But that's what we're interested in. Oh, we do also know the acceleration. Minus 9.81. Okay. All right. So we don't know time. We know distance. We're looking for a velocity. And this is screaming Bumblebee. Screaming at us Bumblebee. Okay. So we got to do our graphs. Sorry about that. Okay. So our graph. Okay. Now we're starting off at 17 here. And we know that it's going to go to 0 if we let enough time pass. However, we're going to catch them at some point here, and so they're going to have some other speed, and we don't know what that speed is. Okay, so this would be if Pat didn't catch them and they went past Pat and they went a little bit higher, then eventually they'd hit 0 as their speed. Okay, now what that looks like in position. Okay, again, so this over here, that would correspond to the apex of the trajectory. So we'd have something kind of like this. But at this point here, they're going to reach Pat right there. So there's 12 meters right there, just like that. Okay. Well, we're trying to find that final velocity. Okay, we got our sketch, we got our graph. Now we're ready to roll on some algebra. And so like I was saying, Bumblebee is a great candidate this time around. So we'll have V final squared, V initial squared plus 2A delta, we'll call it Y since it's vertical. And, oh, look at that. We don't really have to do anything. We'll take the square root of everything. So let's say our final velocity is the square root of VI squared plus 2A delta Y, like this. Now we can put our numbers in. All right. So you can use the radical sign if you want to. You know, on your own paper, it might not matter. Here with the pen, it's just hard to write all that with my special pen. It's hard to write in there on all that crowded little space there. My initial speed is 17 meters per second. Then I have 2 on the minus 9.81 meters per second squared. And then my delta Y, I went up 12 meters. Okay. And let's look at the units real quick. Whoops. This number has to be squared. Boom. There we go. Okay. So if this turns out to be meters per second squared. All right. I've got second squared. I've got meters. So this is also meter per second squared. When I take the square root of them, I'm just going to be left with meters per second. Okay. Nice. Everything works out perfectly there. So my final velocity then is going to be, when I run all those numbers on that, is 7.32 meters per second. Okay. So there we go. All right. So they're still moving pretty quick once they get to Pat. Okay. And so we might anticipate they'll go quite a ways past Pat. And, you know, we could work that out with Bumblebee if we wanted to. I don't really care to at this time. but we could do that. All right, let's look at another scenario. Oh, you know what? Now we're going to do that. Now we're going to find out how high they go. Okay. So Sam tosses the keys, same initial speed, 17. They're going to go past Pat. They're going to go over Pat's head. All right. And then we're going to figure out how far over Pat's head are the keys going to go after Sam throws them. Okay. So we'll make our drawing. Okay. And we still know that we're at 17 to start with. It's going to go up. Okay. And here's where Pat is. So I'm going to say this delta y is 12. All right, but it's going to go a little bit further here. So I'm going to call this y2. We don't know how much further that is. And then right here is where they're going to stop moving. Okay, and I don't know any of these times. But we do know that the acceleration is g. Okay, minus 9.81. Okay, and our pictures are going to look just like they did last time. All right, except now we're starting out at 17 here, and we are gonna go straight down to 0. Okay, and somewhere along here, that's where Pat is, and they're gonna go past Pat. Okay, and then the keys, same thing. They're going to go something like this. All right, but I know when they're here at Pat, they're 12 meters up in the air. So by the time they stop, I've gone just a little bit further, and we don't know what that is right there. Okay, so we're going to try and find that. If we can get that value, whatever it is, then we can use that. We'll subtract 12, and we'll be able to get how far above Pat that the keys went. Okay. All right. This is a great one for Bumblebee once again. Okay, we did our sketch. We did our graph. All right, Bumblebee. Let's roll it out here. So we've got V final squared, V initial squared plus 2A delta Y. Okay, and we're looking for our delta y. So our delta y, okay, is going to be v final squared minus v initial squared over 2a. Okay, and get some numbers in this thing. So the final velocity is going to be 0. We're starting off at 17 meters per second. Then we're divided by 2 times minus 9.81 meters per second squared, that sort of thing. Okay, and okay, and so what we're going to get then in this case, delta y is 14.7, like so. Okay, 14.7. Now, the thing we have to be just a little bit careful with is, what is that 14.7? Is the 14.7 our y sub 2 like in our diagram? No, it's not. The 14.7 is actually this whole distance along here. Okay, so that means y2 we're going to actually have to subtract off. So y2 is going to be that 14.7 minus the 12. Okay, so it's 12 to get to here, 14.7 there. We need the difference in those. So the amount that it goes above Pat's head is 2.7 meters. Okay, just like that. Put a 0 on there. Okay, now let's talk about sig figs super quick. This is one of those things. We did an arithmetic process, and number of sig figs can change on that. So in my equation here, I got 3 sig figs, but we got to look at the weakest link. The weakest link is the tenths unit. So I can't go any more than that. So I got reduced to only 2 sig figs when we did this. Okay. All righty, there we go. Okay. So we did it. We solved it. Evaluate. Okay. We only threw it up a little bit faster than we did before. And as a result, it went up just a little bit higher than it did before. And so that seems reasonable. That seems reasonable. We don't get any red flags if, it ended up being, something like 147 meters. When we only threw them a little bit faster, we might suspect something had gone wrong in our calculation. But everything looks pretty good there. Okay. All right, there we go. That's the end of these couple videos. So what I'm going to do next is I'm going to do a little bit of stuff with some calculus so you can get an idea of what I expect you to be able to do. Okay, what you're going to be expected calculus wise. Okay.